In this lecture, we use the machinery that we've developed in order to prove another and very flexible and powerful matrix concentration inequality, the matrix version of Bernstein. And in fact, we've already seen this. We've already used this 2 times. We used it in our discussion of spectral clustering, and we also used it in our discussion of randomized linear algebra. So the theorem says the following. Let's consider random matrices that are independent and Hermitian. So unlike the matrix Chernoff bound, I'm not assuming that they are they're semi-definite. But note how much more general this is than the first result that we had, which was a Gaussian matrix series. So let's also assume that these are mean 0. So in applications, this is typically a very simple condition to get around, because we can always subtract off the deterministic mean. And let's assume, similarly as we did with matrix Chernoff, that the largest eigenvalue is uniformly and with probability 1 bounded above by R. And as before, let's let Y be the matrix that's the sum of the xk. So we want to understand, get a hold of the largest bounds on the largest eigenvalue of Y. And we're going to do it in terms of the following variance parameter. So let's let sigma squared be defined as the norm of the expected value of y squared. So you'll recall that this is what we used for spectral clustering. Then the theorem says the following: the expected value of the largest eigenvalue of y is bounded above by 2 sigma squared log d, all under the square root, plus 1/3 r log d. Recall that d is the dimension of the matrix. So these are all d by d, and of course y is a d by d matrix. Furthermore, we have these tail bounds, probability that lambda max exceeds t is bounded by d times e to the minus t squared over 2 divided by sigma squared plus rt over 3. So how are we going to prove this? This is very similar to the Chernoff bound in that if we look at the primitives here, we don't want to use, we know that we have something that looks like the trace of log exp e to the theta xk, and we don't want to use something like this in our bounds. We don't want to use that. So in matrix Chernoff, what we were able to use is only the expected value of x. Okay, so recall for matrix Chernoff, the primitive that we used was basically expected value of x. So we bounded the expectation, we bounded the MGF, and then the cumulative generating function in terms of a function of expected value of x. But here, and this always comes back to what the assumptions are. So here what we're going to do is bound the cumulative generating function in terms of expected value of x squared. And the point is that we need this anyway in order to compute sigma squared. Another way to look at it is that the bound that we get on the cumulant generating function, because we're not assuming positive semi-definiteness, as we had for matrix Chernoff, is going to involve an expected value of x squared. And that's why the theorem requires controlling the parameter sigma squared. So that's another way to look at it. So we're now ready to give the key lemma that parallels the lemma that we used for matrix Chernoff. key lemma requires bounding the moment generating function and cumulant generating function. And it says the following. So let's suppose that X is a random Hermitian matrix, just as in the theorem. So in other words, expected value of X is equal to 0, and the largest eigenvalue of X does not exceed R with probability 1. Then, for theta between 0 and 3 divided by R, we have the following bound on the MGF. So the expected value of e to the theta x. So note again, same comment as we made with matrix matrix Chernoff. These are e to the theta x, and its expectation is a matrix. So this is a semi-definite ordering. So it's before in the semi-definite ordering, e to the theta squared over 2 divided by 1 minus r theta over 3 times expected value of x squared. And then we can get a bound on the log of this. So the cumulant generating function, again a matrix, is bounded by just what's inside. Theta squared over 2, 1 minus r theta over 3 times expected value of x squared. So we need to be very careful in our arguments of noting what preserves the semi-definite order when we're looking at scalar functions of matrices. Okay, so proof is as follows. We start with the following rewriting of e to the theta x. This is just equal to I plus theta x plus e to the theta x, and I'm going to subtract off what I added, minus theta x minus I. And I'm going to rewrite this as the identity plus theta x plus x times f of x times x, where I'm defining x as a function on the line is just equal to e to the theta x minus 1 divided by x squared for x different than 0, and then we can just take the limit and write that f of 0 is equal to theta squared divided by 2. So note that we're using the fact that that x is Hermitian here. Okay, so it's easy to check that that f is increasing because its derivative is non-negative, and so this means that f of x is less than or equal to f of r as long as x is less than r. And now how does this apply to us? We use the fact that the eigenvalues of the matrix X do not exceed R. This means, so recall that we spent some time discussing when this holds, and in particular when this holds for matrix functions. So we define matrix functions, so you should look back at the first lecture because this is important to write this implication, even though semantically it looks obvious. So this implies that the matrix function f of x is behind f of r times the identity in the matrix order. So continuing, we get the following, that e to the theta x is less than, in the matrix ordering, I plus theta x plus x times f of r times the identity times x. See, I've substituted that f of r times the identity for f of x. But then this is just I plus theta x plus a scalar f of r times x squared. So basically, I was using this inequality. We eliminated the conjugation. By conjugation, I mean we eliminated, we replaced this term by something that, by just f of r times x squared. Okay, so if we now take expectations of both sides, we have that the MGF, which is again is a matrix, is bounded by I plus f of r, which is just a scalar, times the expected value of x squared. This is starting to get a little bit closer to what we need. We see this term expected value of x squared. Okay, so now we need to bound. We'll bound this term in the following way. So recall the definition of f of r. So f of r is equal to e to the r theta minus 1 divided by r squared. And now let's write the Taylor expansion for e to the r theta as if it were a function of theta. So this is equal to 1 over r squared times minus 1 minus r theta times the expansion of e to the r theta plus the expansion of e to the r theta, which looks like 1 plus r theta plus the sum of k bigger than or equal to 2. I'll copy it down on the next line here. But my point is that the first two terms cancel. So f of r is equal to 1 over r squared, which we factored out, times the sum from k equals 2 to infinity of r theta to the k divided by k factorial. So now we're going to use the following bound. So now let us use the bound that for k bigger than or equal to 2, k factorial is bigger than 2 times 3 to the k minus 2. So you can check that this identity is this is indeed true. So using this tells me that f of r is less than or equal to theta squared over 2 times a geometric series. I want to get that factorial out of there so that I have something that I know how to sum. And that's what we've accomplished. So this is equal to the sum from k equals 2 to infinity of r theta to the k minus 2 divided by 3 to the k minus 2. This is a geometric series, and you can check just using the standard formula that this is equal to theta squared over 2 times 1 minus r theta over 3. So again, summarizing what we have, we've seen that expected value of e to the theta x, this is the MGF, is less than I plus f of r times expected value of x squared. And we also showed that f of r is less than or equal to theta squared over 2 times 1 over 1 minus r theta over 3. So putting these things together, we get that expected value of e to the theta x, that's the MGF, is behind in the semi-definite order I plus theta squared over 2 divided by 1 minus r theta over 3 times the expected value of x squared. And now, using the identity 1 plus a is less than or equal to e to the a, and again we have to argue why the semi-definite order is preserved. I get that this in turn is less than e to the theta squared over 2 divided by 1 minus r theta over 3. And this is exactly what we wanted to show. So this is the MGF bound of the lemma. And then for the CGF bound, we use the fact that the log preserves the semi-definite order. This is something that we had discussed. We had discussed in the first class. So now we're ready to basically plug this bound in to the master bounds. Again, this is very similar in terms of the procedure to what we did to prove the matrix Chernoff bound. So we do that right now. So let's see what we've got. So recall the master bound tells us that expected value of lambda max of y, which is just the sum of xk, is less than or equal to the infimum over positive theta 1 over theta log trace exp sum of log of expected value e to the theta xk. And this lemma has exactly managed to bound. This is the CGF. So let's plug in what we have from the lemma. So the lemma implies that the log of expected value of e to the theta xk is in the semi-definite order less than, again we'll use just a placeholder here for that expression, so g of theta times expected value of xk squared, where g of theta is that complicated expression that we derived. Theta squared over 2 divided by 1 minus r theta divided by 3, and this only holds for theta bigger than 0 and less than 3 over r. So plugging this in, we get that the expected value of lambda max of sum of xk's is less than or equal to the infimum, and now not over all theta, but only theta in this range. 0 less than theta less than 3 over r of 1 over theta log trace e to the g of theta sum of expected value of xk squared. And this is exactly expected value of y squared. So we're getting and this is the parameter that we have. And now we use our usual tricks. So we now use our usual bounding techniques. One of them is to bound trace by d times the largest eigenvalue. And then we know that we can exchange the lambda max with the exponent. So again, taking this slowly, this is now less than or equal to the infimum over theta in this range, I won't keep writing that, of 1 over theta times the log, and instead of the trace, d times lambda max of what's inside. What's inside is exp g of theta expected value of y squared. Now I can exchange lambda max and exp. Again, if you're unsure of that, make sure you understand that properly. And it comes just from the definition of what the exp function is. So this is equal to, this is not a bound, this is equal to inf of theta, again in the range 0 less than theta less than 3 over r, 1 over theta times log of d, and now lambda max has gone inside. So I have exp, and in fact it can go inside the g of theta because because as we've said, lambda max is a homogeneous function. So this is exp of g of theta times lambda max of expected value of y squared. But this is exactly the parameter in the theorem, sigma squared. So finally we get that this is equal to the infimum over theta in the range 0 less than theta less than 3 over r times log d over theta plus theta over 2 1 minus r theta over 3 times sigma squared. Okay, and this is something that in principle we could minimize. This is just a function of a scalar variable, so we could just minimize this and choose the best theta. And indeed, if we do that, we get the result of the theorem. So minimizing over theta gives the result. Gives a result for the bound on the expectation. So we also have a bound on the tail inequality. And again, we can obtain this by starting from the master bound. So the master bound tells us that the probability that lambda max of y is bigger than t is less than or equal to the infimum over all theta positive e to the minus theta t trace exp sum of log of the moment generating function e to the theta xk. So now we repeat the same steps. Repeat the same steps, i.e. from lemma, use the bound for the cumulant generating function, which is this, and then use the same standard bounding techniques that we used above. In other words, bounding trace by d times lambda max and so on. And in precisely the same manner, we get that the probability that lambda max of y is bigger than t is less than the infimum over theta in the range 0 between 0 and 3 over r d e to the minus theta t e to the g of theta sigma squared. So again, this is an infimum, and we could optimize this. So we can now optimize over theta. To get exactly what we gave in the theorem, we can instead use theta equals t divided by sigma squared plus rt over 3. And you can check that this is always in the right bounds. And this results in a clean, the point of this is just getting a cleaner bound. And plugging in, we get the bound stated in the theorem. So this completes the bound of matrix Bernstein inequality. A few notes are that, as with essentially everything that we've said, these extend to general square matrices rather than just Hermitian matrices. This is a very flexible. We can remove the Hermitian assumption. And in general, Matrix Bernstein is a very flexible tool, and we'll in the future lectures look at a few more applications of it.